Root finding is one of the most common procedures used in computational studies. Newton's method is one of the simplest and easiest methods for performing root finding. The question it solves is this: given some function f of x, at what values of x does f of x equal 0? Here's a sample plot of an f of x that passes through 0, otherwise known as a root or a zero crossing. And sometimes it's easy to find the root. For example, this is a function x squared minus 1 that has a bowl shape, and it has two roots at minus 1 and plus 1. That's easy to find analytically. But more often, it can be quite difficult to find roots. And in fact, this seemingly simple function, sine of x plus x squared plus 1, is very difficult to find the roots for. It's situations like these and many others where we have to resort to computational methods, and that's where we use Newton's method. The procedure is like this. Here I've plotted an example function f of x against x with a root which we would like Newton's method to find computationally. The first step is to set a counter k equal to 0 and make an initial guess for x of k and evaluate the function f at that initial guess to yield y of k. Here I've chosen an x of 0 and a y of 0 arbitrarily. The second step is to evaluate the slope of the curve, df dx, at that candidate root location x of k, which as a shorthand we'll call j for Jacobian, which is just a shorthand term for partial derivative. And it's shown here with a little tangent line. The third step is to extrapolate a straight line from that tangent all the way down to y equals 0, the horizontal axis. This is going to yield the next candidate location for the root, x of k plus 1. The fourth step is to test whether the candidate root location, x of k plus 1, is considered close enough. If not, then increment k and repeat the procedure starting from step 2. If it is close enough, then we can end the steps of the procedure. Here I'm going to draw in a few additional values, x of 1, y of 1, evaluation of the slope, extrapolation to x of 2, y of 2, and so on, just to show the procedure getting closer and closer to the actual root. I've left off some details of how the extrapolation is performed, so let's take a closer look at j. The slope is being used for a straight line, delta y over delta x, where delta y is y of k plus 1, the next candidate location for y, minus y of k. That quantity is divided by x of k plus 1 minus x of k. Now, since we extrapolated the line down to the horizontal axis, y of k plus 1 should be 0. And that allows us to solve for delta x. It's just 1 over j times 0 minus y of k. And therefore, x of k plus 1 is just x of k minus 1 over j times y of k. As for the test for close enough, we evaluate y of k plus 1, which ideally should be close to 0, by just plugging our candidate root location into the function f. We test whether the absolute value of y is close enough to 0 against some tolerance, which is a value that we set for whatever counts as close enough. So far, this procedure has been described in terms of scalar values for f and x, but we can almost use the exact same procedure for vector-valued f and x as follows. First of all, we need a partial derivative, which is now going to be a matrix. And the way that's evaluated is first df1, dx1, and then underneath that df2, dx1, and so on, so that the first column is just the partial derivative of f with respect to variable x1. And then continuing across the matrix, in the first row we have df1 dx2, and then at the end of that row df1 dxn. So going across the matrix, we're evaluating partial derivatives with respect to different values of x, and going down the matrix, we are seeing different values of f. Given a matrix for J, solving for delta x is now a matter of solving a linear system. J delta x is equal to minus y of k, and one way to solve that in MATLAB is to solve for delta x is equal to j backslash negative y. The backslash is MATLAB's procedure for solving a linear system. It's more or less equivalent to just taking the inverse of j, although computationally it's generally considered superior to use a linear solve procedure rather than explicitly evaluating the matrix inverse. Now that we know how Newton's method works, it's also instructive to consider the cases where things can go wrong. Here I've drawn a function f of x versus x, which intentionally is going to cause problems for Newton's method to find the root of interest. One of the things that can go wrong is a slope of 0, which first of all is problematic computationally to divide by when we're looking for delta x. But second, even if the slope is not 0, it can be problematic because it can cause Newton's method to extrapolate in a bad direction or to extrapolate too far. Another potential issue with Newton's method is if there are multiple roots in the function. Multiple roots may or may not be relevant to the question at hand, but most importantly, Newton's method is really intended for finding one root. When there are multiple roots, it usually requires some care and possibly some hand tuning to find and separate the distinct roots. The solution to all of this is simply that for Newton's method to work well, you need a good initial guess for the candidate root location. Otherwise, you risk the possibility of poor convergence or even converging to a wrong or nonsensical value. Nevertheless, Newton's method is perhaps the most popular method for root finding. It's easy to code and it's quite effective. This concludes our discussion of Newton's method.